Okay, so far we have angular versions of position, velocity, displacement, acceleration. And those analogs were defined in exactly the same way that we defined the linear ones. Can we keep going? After defining position, velocity, acceleration, displacement in chapter 2, we used them in multiple dimensions in chapter 3, but then in chapter 4, we defined force. And then in chapter 6, we defined kinetic energy and work. And then in chapter 8, we defined momentum. Can we just keep doing motion analysis with these new angular flavored variables in exactly the same way as we were? I mean, you're modifying them for use in the angular case, and the answer is yes. And that's what the next few segments are about. The first one I'll start with is energy, because energy is scalar. And that makes things really nice when we're dealing with these quantities that point in strange directions. So, let's talk about some object, some shape, something, the lid of a jar or a ceiling fan or whatever. I'm gonna draw it so it looks like, I don't know, let's see, some square cross section and maybe another square, so it's got some shape, I don't know. It's an arbitrary shape, it doesn't matter. And I wanted to rotate around an axis through this point, perpendicular to this axis. I'd like it to rotate counterclockwise with angular velocity omega. So again, we're taking some funky shaped object and we're asking for it to rotate around an axis through a point somewhere along it, which looks like that. What is the kinetic energy associated with this kind of motion? Because this is motion. The object isn't doing this on its own. Presumably someone has to go affect it somehow. Apply a force, do some work, I don't know, something. So the fact that it is moving now, is in motion, such that we can talk about omega, means that it must have some motional energy. Let's talk about this little cube of mass right here. So somewhere in the object, it has a radial distance from the axis of rotation. Let's call it r sub I. That's a vector. This is lowercase r. There we go. And this little chunk of mass has some mass m sub I. We know if it is rotating with angular velocity omega, we know that it has some linear speed in the circular path around this axis. So we could write that the velocity of this ith piece is omega r. Omega ri. I don't need the vectors because I'm about to calculate the kinetic energy of this piece. I mean, technically, yeah, I need the cross product. But once I find it, I'm just going to take the magnitude of that. So the kinetic energy of this ith little piece of mass as it orbits in a circle around the axis of rotation, 1/2 MIVI squared. Okay, and there are, I don't know, n of those masses scattered throughout this object. So if I wanted the total kinetic energy of this object rotating, I would need to add up the kinetic energies of all the individual pieces. So let's do that. MIVI squared. And now it's clear that I, in this case, doesn't stand for initial, it stands for index. Every mass in the object has a little deli counter butcher ticket, and we now serving mass number 3. What is your mass? How far away are you from the axis of rotation? I can calculate your speed that way, and then I can calculate your kinetic energy. Okay, now serving mass number 4, come on up. What's your mass? How far away are you from the axis of rotation? I can calculate your speed and then your kinetic energy. And mass number 5, all of the masses in the object, add them all up. That's the total kinetic energy. 1/2 and omega squared, those are constant across this summation. Everybody is rotating with angular velocity, omega. So we could pull 1/2 outside of the summation, and we could pull omega squared outside of the summation. Our formula for kinetic energy used to look like, well, it still does, but our formula for linear kinetic energy looks like 1/2 mv squared. We just used that. But here we've written a thing that looks like the total kinetic energy of a rotating object is 1/2 some junk omega squared. And I don't know, call me crazy. It looks like this some junk lives where the mass would live in the linear case. Do we need, I didn't see this coming, do we need to modify mass according to whether we're rotating or not? That seems like a lot. Mass is mass, isn't it? But remember that what mass is actually doing is quantifying inertia. Got a ruler here. Asking for the ruler to rotate around an axis along its length, perpendicular to the cross section, is an easy ask. It likes to do that. It almost it'll almost do it on its own in a way. Asking for this ruler to rotate around its end, around an axis perpendicular to the length of the ruler, is more difficult. You know, if I cause it to rotate around this axis, it'll rotate once, maybe, oh wow, a lot of times that one. Maybe 10 times in the half a second that it takes me to catch it. If I want to create an angular velocity around an end such that it'll rotate 10 times before I catch it, I have to exert I have to exert myself. It's harder to do because this mass over here has to move in a very large circle compared to the mass that has to move in a circle this way. The farthest the mass is away from the axis of rotation is only, what, half a centimeter maybe? Here, it's 30 centimeters away. And that mass all the way at this end has to have a greater velocity because it's farther away, which means I needed to give that mass, that piece of mass way out at the end, comparatively way more kinetic energy than I had to give the mass at this end. Changing the kinetic energy of some mass I had to do more to get it to rotate the same way. So apparently, it matters how the mass is distributed relative to the axis. That we don't only care how much mass there is, we care what kind of motion we're going to try to get it to do, which I guess makes sense. Taking the ruler and moving it from here to there is the same proposition whether we orient it this way or whatever. You know, a translation of the ruler's center of mass from here to here is the same whatever the orientation of the ruler is, but a rotation around an axis is not the same rotation around a different axis, right? Rotation around an axis along the ruler is a different thing and easier to do, less inertial, right? The ruler is happier doing that than rotation around an axis through a different point in a different, orientation with respect to the object. That's this. How altogether, how is the mass distributed relative to the axis of rotation? Remember, this R is not relative to an origin. I don't have a coordinate system on here. It's relative to the axis around which we are rotating. And it is very much a radius. It's not a position vector that points in any weird direction. These masses undergo circular motion. What is the radius of that circular motion? That's what we're talking about here. And that has to do with where they are relative to the axis around which we're rotating. Makes me think that this thing in parentheses I need to define. I gotta give it a name. It looks to me like angular mass, which is a weird thing to say, but rotational mass distribution, if you like. I like that. Rotational mass distribution. How are we allocating the mass that we have relative to the axis of rotation? I would like to call the other name, the name that we see in the textbook. Moment of inertia, capital I. somewhere along the way, I picked up a habit of using 2 vertical bars for the capital I in moment of inertia. You'll see that from me sometimes. I just mean a capital I. I'm just trying really hard to keep it from looking like an L or from like a number 1 or anything like that. Capital I, moment of inertia. Inertia makes sense. What the hell is moment? Moment is an old word that comes from engineering. We've actually already calculated the first mass moment, and it's center of mass. We multiply each position times each mass, add them all up, and then we divide it by the mass to get an average. But that numerator is the first mass moment of position. This is the second mass moment of position. The second mass-weighted product with position. Moment, rotational inertia. The textbook calls it moment of inertia. So we can redefine our kinetic energy of rotation. 1/2 I omega squared. What if it's not a discrete object? What if we don't want to have, 1,000 little chunks of mass? What if we're talking about some actual object, some continuous object? We're going to have to do calculus. I'll write it this way: r squared dm, because those masses are getting infinitesimally small. That's the differential part. R squared dm as an integral over the volume of the object. Anytime we want to do that, we want very much to leverage the symmetry of the situation so that we can do what we did with the path integral and rewrite this as a single integral in a single scalar variable. And then we can integrate and be fine. We'll practice that this week, but we needed to see the definition here. The textbook provides a convenient table of sort of, I guess, regular objects, like a very thin rod of length L has a known moment of inertia. We can go look it up in the table. A solid sphere has a known moment of inertia. We can look that up in the table. If there's some other kind of object, or maybe it's not uniform, maybe the density isn't uniform throughout or something like that, then we'll have to calculate it. But we have developed a rotational mass, an angular mass, and a rotational kinetic energy. We are on a roll. If we are going to talk about a rotational kinetic energy, I really also want to talk about a rotational work so that we can write the work energy theorem again, just for rotation. But in order to talk about a rotational work, I need to talk about a force, because work is force dot displacement. So I need to talk about rotational force in order to talk about rotational work so that I can write the work energy theorem. And to do that, we're on to chapter 10.